proportional sign, then we get constant of proportionality K. Okay, but there is a negative sign. Why this negative sign is there? Because direction of heat transfer, that is Qx and dt by dx are opposites. To balance their sign, there is a negative sign. Okay, so now we'll go to the convection now. In case of convection, governing law is Newton's law of cooling. Newton's law of cooling tells us that heat transfer in convection is proportional to the area. You can see here area, like the fluid is flowing over the plate. This plate is having the temperature Ts higher than the surrounding temperature T infinity. Okay. So heat transfer is proportional to what? The area. Bigger the area, more is heat transfer. Okay. And temperature difference between the surface Ts and T infinity. That is the surface temperature, and T infinity is the surrounding temperature. So this is the law for convection, that is called as Newton's law of cooling. Now I'll move to the radiation law, that is called as Boson law. Here heat transfer is proportional to the area as well as temperature. And here comes one constant, which is an absolute constant. That is, its value is fixed, 5.67 into 10 raised to minus 8 watt per meter square, Kelvin raised to 4. Okay. Now what happens? Radiation is surface radiates. So there is a actually we can say there is a net heat exchange. Okay, so we can write that heat exchange by the more appropriate equation. Okay, so we can write heat transfer like here. Surface is radiating to the enclosure. So we can write heat transfer by radiation as area A1. So it is emitting from the area A1, then emissivity of surface, then sigma T1 raised to 4 minus T2 raised to 4. So it is a temperature heat exchange between the surface, which is at T1, and the enclosure, which is at the T2. Okay. So in the radiation, we should also know the what is called as the shape factor and the emissivity of the surface. Now, as I mentioned, when we go for finite difference, we should know how this particular equation came into the existence. So, what I decided today to first derive the equation and then go for finite difference method. Okay. So what happens? We want to derive the equation. For that, what we do, we consider very small element, like you can see here. It is an element along the x-axis, then y-axis, and then z-axis. This is the element. Okay, the element is having the sides dx, then dy, and the dz. Okay, and this is element is generating the heat at the rate of q dot. Q dot is heat generated watt per meter cube. Okay, so it is a heat generation per unit volume, we are saying. Okay, now let us assume that material is non isotropic, means its conductivity along x direction, y direction, and z direction are different. There are some materials, like you can take the material like wood, where k is not same in all the directions. Okay, so here we have for starting we have decided that it is conductivity is different in the different direction. Okay, Now, from what basis we have derived this equation? So please understand that the basis is the first law of thermodynamics. Okay. What is the basis for deriving this equation is the energy equation, that is the first law of thermodynamics. Please understand, first law of thermodynamics, there are two mathematical equations. Many people, if you ask, they say first law of
Excuse me,
thermodynamics
Sachin.
means energy can. Yes, yes. Can you
We are
hear
at
me?
the slide number 2. So are we correct? Are we going at the right slide or there's some mismatch?
There nine is slide number nine. It is showing nine.
No, we are at, we can see only slide number 2, where we
Okay.
have the mode of heat transfer actually.
So what I will be do, I will again join. Maybe some problem. Okay.
Yeah, that might be a
Sharing.
problem.
I will try to share again. But if it not happen, I will disconnect and again connect.
Only first slide is there.
Uh, yeah, yeah.
Most of it transfer.
Okay. Can you see now?
Yeah, we are on this third slide, that is modes of this conduction, convection, radiation.
No, no, it is different. I think it is showing. Uh, can you see the slide number five?
Uh,
Slide number five.
Not yet, actually.
Hello.
Not yet.
Maybe I switch on the marker now, that created problem. I will disconnect and again connect maybe.
Okay.
I'll disconnect from meeting. Hello.
Yes.
I will just share now. Maybe I will not use the pointer. Okay.
Yeah, that might be creating some problem.
Yeah, yeah.
We actually never know what thing is creating the problem.
No, no. When this Google Meet, I have always trouble. Zoom is very comfortable.
So, which platform do you use? Zoom there.
Yeah.
Okay, okay, okay.
I'm trying to share now.
Because each platform to platform something change.
Now, are you able to see the PPT number
Uh,
three? Hello.
just a bit. Presentation is just coming. Yeah, it's slide number 3.
Slide number three.
Yeah.
Oh yeah. Okay. Uh, can you see this slide number six?
Mm,
No, there is slide number
no,
3.
it's only 3.
Yeah.
Is it a
3.
copyright slide number 3, which is not good?
Mechanism and transfer.
Uh,
So you can probably you can send the slides to me. I can share from this side here if
okay. I will just send you by WhatsApp. I just sent the PPT.
Sending to me by email.
WhatsApp, I send WhatsApp.
Okay, okay,
Or
okay.
shall
Let's.
I send by email?
It's just 1 minute. It has come, and I'm just sharing it. On.
Can you see my PPT now?
Yeah. On the screen.
Yes.
From
Yes. Can you see
uh,
on screen? On screen.
let's see. No, actually.
I am to send by email.
Yeah, yeah, I got it. I'm just transferring it to the computer actually. Yeah, we can see your PPT now. I say we are on front slide. So I will share the presentation from the my and will that be fine?
Okay, yeah, no problem.
Okay, okay. So I'm just opening it only. So Is visible now?
It is not still visible. It's telling that
No,
Raj,
it's
now it
visible.
is visible.
So you tell me which slide should I go actually. I will
You
try
go
to
to
scroll
the
all
slide
back.
number 4.
Fine. So
Yeah.
this is your phone.
Yeah. If, one more enter now. Let display full content. Yeah. Okay. So actually we started with this that in the case of conduction, the governing equation is Fourier's law. It tells that heat transfer by conduction is proportional to the area perpendicular to heat transfer and the temperature gradient dt by dx. Okay. When we remove the constant of proportionality, k comes, and k is a material property. It is constant for given material, but it is a material property. And negative sign is used as a direction of heat flow q, and dt by dx are opposite. Move to the next slide. Then we'll move to the Newton's for convection. There is a law called as Newton's law of cooling. So this convection is because of fluid motion. Okay, like you can see here, there is a plate of area A having the temperature Ts, and there is a flow of the fluid over this. Okay, surrounding temperature is T infinity, and now because of temperature difference, there will be heat transfer. So governing law for convection is Newton's law of cooling. It tells that heat transfer by convection is proportional to area and proportional to the temperature difference between the plate and the fluid temperature. Okay, and there comes the constant of proportionality H. Here, constant of proportionality, the constant of integration is not constant. It is a complicated function of material property, then a flow, then geometry. Okay. Now we'll move to the third mode of heat transfer. Next slide, slide number 6. That is the radiation. So radiation comes into picture when the temperature difference is a big. Okay. So law governing is the Stephen Boltzmann law. It tells that heat transfer by radiation is proportional to the area and the fourth power of absolute temperature. Okay. In case of convection and conduction, we are not telling whether the temperature is absolute temperature or whether it is in the degree Celsius. Okay, because there is a difference, and even if you write in Kelvin, ultimately it will become 273 will get cancelled. But here, in case of radiation, we have to take in the Kelvin only. Okay. So here constant of proportionality is the absolute constant. That is the sigma, Stephen Boltzmann constant. Okay, it is a 5.6 into 10 raised to minus 8. Okay. Now we'll move to the next slide. Okay, this is absolute constant. You can see here. Okay. Now this is a law which is for single surface, but actually what happens? Each surface radiates. Each surface receives the radiation. So what we have to do is when it is exchanging the radiation, then we have to also both consider both the surfaces. Like here you can see one surface A1 is emitting radiation, and that is received by the one enclosure. In that case, we can write heat transfer by radiation as area A1, then emissivity. We have to take the emissivity of the surface, and then sigma T1 raised to 4 minus T2 raised to 4. Okay. So T1 is absolute temperature of surface, and T2 is the absolute temperature of the surrounding. Okay. So when we deal with the any even for solid, then we come across the different boundary conditions like conduction, convection, and radiation. Okay, so that's why I'm taking this. We can move to the next slide, slide number 8. So what we decided here that we will also not directly use the equation, but we'll also derive the equation that will give the feel for us how the equation came. Okay, when we directly solve the equation, we don't get feel what is the physical significance of it. Okay, so whenever we derive the equation, so we derive the equation for the very small elements and then find the differential equation, and to get value we integrate it. Okay, so to formulate equation we have to consider very small element. Like here I have considered a small element having the side dx along the x, dy along the y, and dz along the vertical direction, that is z direction. Okay, now I consider that this element having the heat generation capacity or Q dot. Heat generation we express basically in case of we express with the watt per meter cube. Okay. Now for deriving this equation, we assume that it is non-isotropic, that is anisotropy. So K, conductivity along the x direction, conductivity along the y direction is Ky, conductivity along the z direction is Kz. Okay. So later on we can simplify that. Next slide. Next slide, please. Okay. Okay. So what we do now, I think go back 10 number, slide number 10. Okay. So now I assume that in particular direction heat is coming from the left as a qx, and whatever heat leaving is qx with the suffix x plus dx. Okay, now we move next, slide 11. Now here we have to use Fourier's law. Please understand that Fourier's law is in the particular direction. Like you know that Newton's second law for force is what? For force, and it is in particular direction. Similarly, Fourier's law is in particular direction. Okay, so we need to write in x direction, y direction, and z direction. Basically, we'll see here in x direction, and similarly, equation will get in the y direction. Now, you write the Fourier's law of heat conduction, that is qx minus kx into area dA, small area dA, into dt by dx. Okay. So this is your heat conducted in. It is what? Heat conducted in. Now we have to similarly we have to write heat conducted out. Okay. For writing this heat conducted out, we take the help of Taylor series. Please understand what Taylor series we will use in the finite difference, that is also taken while deriving this equation. Okay, like suppose we know on the left face value of variable, how will you find the value of variable on the right face? We'll write the value of variable on the left, plus we'll take the derivative. Okay, in that direction, like the direction is x, so I will take derivative del by del x of qx, and then I will write the distance between the two faces. What is distance between two faces? Dx. Okay. So now here we have not taken, we have eliminated even in the proof itself the higher order terms. Okay. So here itself is a one we can say approximation. Okay. Now what is my purpose is here to find the net heat conducted. So what will be net heat conducted? Heat in minus heat out. Okay. So Qx minus Qx plus dx. We'll move to the next slide. We'll move to the next slide. 13. 12. Okay. Okay. 12. 12. Okay. Slide number 12. Okay. So Ix we know it is so net heat conductivity will be what now? Del by del x Qx dx. Okay, because Qx will get cancelled. So we got this net heat conducted. Okay, we know the Qx is minus Kx dy. Now area is what we can see in the diagram. Small area that is dx and dy, that will form the dx into dy into dz will form the area which is perpendicular to Qx. Okay, now you write in the Ix. Okay, and now as kx is a variable, it will not able to come outside. Okay, but if you see dy, dx, dy, dz, these are what constants, so it will come out. Okay, so I get Ix as dx, dy, dz, del of del x, kx, del t by del x. Okay, please understand why kx is not coming out, because we consider it is a variable. If it is constant, then it can immediately come out. Okay, so similarly, you can get net heat conducted in the y direction as dy dx dy dz into del by del y into ky del by del t by del y. Please understand, one question will come, simple question will come in your mind, why we are taking partial differential? Because here the independent variables like what is coming in the denominator x, y, z, t are what? More than one. That's why it is coming in the partial differential form. Okay, we'll move to the next slide, 13. Similarly, we can write net heat conducted in the z direction. That is dx, dy, dz into del by del z into kz del t by del z. Okay. So if you want to write net heat conducted, then I will add up net heat conducted in the x direction plus net heat conducted in the y direction plus net heat conducted in the z direction. Okay. So we got this first term, that is the net heat conducted. Okay. So what I will do now, I will take the dx dy z for common, and other things I will write like del by del x into kx del t by del x plus del by del y into ky del t by del y plus del by del z into kz del t by del z into bracket, and then dx dy and dz. So it is a net heat conducted. Can move further. Slide number 14. Okay. Actually, maybe we skip one slide. There are three components. Can you move previous slide? I think we missed one slide. Something. Go previous, 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 previous one. Okay. I think this is the slide we move. Yeah. Okay. Slide number 9. Slide number 9. Okay. Now, as I mentioned, what is the basis for deriving this equation is the first law of thermodynamics. First law of thermodynamics, there are two mathematical equations. One is for process and one is for cycle. You know this very well. Okay. Now here it is not cycle, it is a process. So we'll use that equation, mathematical equation of first law of thermodynamics. So what it tells us that heat supplied to the system is utilized in two parts. What is the first part? To change the internal energy, and second part is to do the work. Okay. So there are two equations of first law of thermodynamics. First is for process and second is for cycle. So here it is not related to cycle. So obviously we have to use first law of thermodynamics for the process. What it tells in the simple way, so whatever heat is supplied to the system, it is utilized in two parts. One is to change the internal energy, is to change the temperature, and second is to do the work. Okay. Now for for this element we'll write this equation. Okay. Now heat supplied will be in two parts here. First will be net heat conducted, that is a part number one, plus heat generated in the element. Okay, so this is the total will be what, 1 and 2 will be what is supplied to the element. Now on the right hand side we'll see third part is what, change in internal energy, that is third part, and fourth part is what, work done. Okay, now we'll see one by one, that was our aim. Okay, so just we saw, now we can move to the slide number 13. Okay, so we have calculated first part. Okay, that is net heat conducted. Now we have to calculate second part, that is the heat generated. Okay, so move to the slide number 14. Okay, so as I mentioned when we started, q dot is what, heat generated per unit volume. So if I multiply q dot with the volume, then it will, we will get the heat generated. So what I did now, I multiplied the q dot with the volume dx dy dz. Okay, so we have finished part number 2, that is 1 and 2, which is on the left hand side. I will move to the right hand side, like change in internal energy. Okay, we know the what is the formula for this, it is a mcp delta t. Okay, for change of internal energy, what is formula, mcp delta t. Okay, but if you see on the left hand side, what is the unit of heat, it is a joule per second. What is the unit of heat, it is a joule per second in the heat transfer. But if you see mcp delta t, what is the unit, it is a joule. To make it per unit time, you have to divide by del small t. Okay, now how we'll calculate the mass, we'll calculate mass by multiplying the density with the volume, that is the dx dy dz into rho is what, mass. T is specific heat, and del T is what? Del capital T is what? Change in temperature divided by change in time. Why divided by change in time? Because left hand side all the units are joule per second, so we have to make joule per second. We have to divide by the time. Okay, so that is our third part. I will move to the fourth part, that is the work done. So move to the next slide, slide number 15. So please understand here, in case of conduction, work done is there because of change of the expansion of or contraction of the material at particular location. But this work done is a force into displacement. Work done is what? Force into displacement is very negligible, and we neglect here. We make it as a zero. Okay. So we can write now part number 1 plus part number 2 is equals to part number 3, and part number 4 is what? 0. So whatever we got, this is the equation of conduction in the Cartesian coordinate. Okay. Now we'll rearrange this. We'll move to the slide number 16. Okay. So maybe it is copied. Just copied. Okay. Move to the next slide. Okay. So this is our three-dimensional heat conduction equation. For an isotropic material means K is different in different direction. Suppose we consider it is isotropic material, then Kx will be Ky is equals to Kz in all direction. If it is the same, then we can write instead of Kx, Ky, Kz, we will write K. So we got this equation. Now as now it is a constant, it comes out. Okay, like del by del x into Kx in the first line we can see equation number 6. As now K becomes constant, it comes out. Okay, that's why we get the equation now. See the equation number 7. It is the del square T by del x square plus del square T by del y square plus del square T by del z square plus q dot bar k is equals to rho c t rho c by k into del t by del t. Okay. So here we get one quantity called as alpha, that is k by rho cp. It is called as thermal diffusivity. It is the rate at which the temperature penetrates into the body, that is called as thermal diffusivity alpha. I will move to the next slide. Now please understand the importance of thermal diffusivity. It is ratio of thermal conductivity to the heat capacity of the material. Higher the alpha, faster it will penetrate into the body. You can see here on the left hand side, if the alpha is less, you can see the red temperature not much entering in. Okay, but we see on the right hand side where alpha is high, the high temperature is entering much into the body. Okay, so higher the alpha, faster is the penetration of temperature for in case of transient heat conduction. Okay, we'll move for the slide number 19. Slide number 19. Okay. Now, there are different equation. If you eliminate some particular parameter, like if there is no heat generation, then our equation becomes equation number 8. That is the del square t by del x square plus del square t by del y square plus del square t by del z square is equals to 1 by alpha del t by del t. So this equation is called as Fourier's equation. So it is a transient heat conduction equation without heat generation. We move next slide. So another case, suppose it is a steady state heat conduction, but there is heat generation, and then the name of the equation, it is Poisson's equation. So it is del square t by del x square plus del square t by del y square plus del square t by del z square is equals to plus q dot bar k is equals to 0. It's Poisson's equation, steady state with heat generation. Now we'll move to the next equation, that is Laplace equation, slide number 21. In the Laplace equation, there is no heat generation and it is a steady. Okay, so it is called as Laplace equation, which becomes del square t by del x square plus del square t by del y square plus del square t by del z square equals to 0. This is called as Laplace equation, that is the steady heat conduction equation without any heat generation. Now we'll move for the slide number 21. Suppose I want to convert that equation into the steady one-dimensional equation without heat generation. That is the Laplace equation. Okay, only in one direction. Then it will become what? Del square t by del x square, because del square t by del y square and del square t by del z square 0. So it will become del square t by del x square equals to 0. But as it is a one-dimensional, what will happen now? Independent parameter is not more than 1. So it will become what? Del square t by del d square t by dx square equals to 0. Okay. So because only one independent parameter, it will become the exact differential equation. I'll move to the next slide. Now, for the two-dimensional heat conduction, so steady-state equation will become del square t by del x square plus del square t by del y square plus q dot by k equals to 0. I will move further. This for two-dimensional. Okay. Now, we just saw how the equation was derived, how the Taylor series was used. Itself, approximate Taylor series was used while defining qx plus dx. Okay. Now, what happens for 1D case? We can find the exact solution. Okay, but analytical solutions are not available for every cases, and they are only available for limited ideal cases. Okay, so what we do is we use numerical techniques, which gives approximate solution. Okay, and this approximation, whatever error is there, we can minimize by making or taking very small elements, small size elements. Okay, so what we do here in finite difference method, properties or variables are determined at discrete points, and we call it as a nodes. Okay, so if you see the concept, finite difference concept is brought from definition of derivative. There are two ways. We can say directly from derivative, or we can also take the support from Taylor series. Okay, same thing we will get. Okay, so first derivative at any point is what? It is nothing but it is a slope of the tangent to the curve at that point. This is the concept we use. Okay, we can represent derivative by the slope of the tangent to the curve at that point. Okay, so we'll move further. Now in the diagram, you can see in the diagram, I will not move further. So there is a function which is shown by the curve. Okay, you can see exact tangent. You can see there, but if you take tangent by the forward difference, okay, and you can take by backward difference, and by center difference, you will find that these slopes are different. Means what? It is an approximation. Okay, whatever we write, it is approximation, and it is not always you can say exactly to the exact tangent. Okay, so there is some approximation. This approximation, you can say error, we can minimize by taking small and small elements, so it will reach slope to the exact slope. Okay, I'll move further. Slide number 25. So what we do, we replace differential equation by algebraic equation, which will be we can say it is a difference of quantities. Okay. So what we do, we can say we split the domain or the volume where we want to do the calculation with the small elements, and wherever this small elements corners, we can say they are called it as a nodes. Okay, you can see here in the diagram, uh, along x, I will say it is m, and along the y direction, I will say it is a n. Okay, so the first node will be in the diagram, right hand side. You can see it is m minus 1, then the next will be m, the next will be m plus 1, and it will be constant. Okay, now we'll go vertically. So bottom node will be n minus 1, then the main node will be n, and then if you move up, it will be n plus 1. Like this, there is increment in x and y, we can say uh, identifier. Okay, okay, we can move now. And this element will have the some size like delta x along x direction and delta y along the z direction. Can move to slide number 26. Now, as we know that here our interest in the conduction, it is a second order, that is the del square t by del x square equation. So we have to find its equivalent finite difference equation, algebraic equation. So what I'm doing here, I'm just writing the derivative, that is the del t by del x at m minus half, okay, and n, okay. Now you can see here in the diagram, the first node is m minus 1, middle node is m, then next node is m plus 1. So when I say if I want to take the slope, then what I will do, I will take at the midpoint, that is the m minus half. Okay. First slope I will take at the m minus half. Next slope I will take at the m plus half. Okay. So it will more approximate. We already seen in the while starting that if you take at the midpoint, the slope is more we can say accurate. Okay, because it will represent more accurate slope for that line. Okay. So just now we like the del t by del x at m minus half comma n. So it will be this m value, that is the t m comma n minus t m minus 1 comma n divided by the distance between these two nodes is what we can see the delta x. Now write derivative at m plus 1, that is del t by del x m plus half n. So it will be t m plus 1 comma n minus t m comma n divided by the distance between two nodes is delta x. Okay. Now we know that second derivative is the derivative of first derivative. What we know is that second derivative is derivative of first derivative. So we'll move further, slide number 27. Okay, so you can move 20 slide number 28. Okay, so we know that second derivative is what? Derivative of first derivative. So we'll just now write down in the same way, del square t by del x square is equals to del t by del x at m plus half minus del t by del x at m minus half divided by distance between that. You can see the distance is again what? As both are midpoint, again their distance is what? Del x. So divided by del x. Now we put the values here, you will get now del square t by del x square is equals to t m plus 1 minus t m minus t m minus t m minus 1. Okay. Now minus minus will become plus. We can move further now. Next slide. So we get del square t by del x square is equals to t m plus 1 minus 2 tm plus tm minus 1 divided by del x square. So this is our approximation of second derivative, okay, that we'll use in our equation for FDM. Okay. Similar equation we can obtain from the Taylor series. Please understand what we written here can also be obtained from the Taylor series. Okay. So we can move further now. Slide number 30. Okay. So now let us see 2D heat conduction equation with the heat generation. Steady, it is a steady 2D heat conduction with heat generation, which will be del square t by del x square plus del square t by del y square plus q dot by k equals to 0. Now I can write del square t by del x square. It is t m plus 1 minus twice m plus t m minus 1 divided by del x square. Now next second derivative will write del square t by del y square. It is t n plus 1 minus twice tn plus t n minus 1 divided by del y square, because it is in the y direction. plus q dot by k. Q dot by k is what? It is a constant. So we are not writing any derivative. Okay. Now move further. Slide number 31. So you can appreciate that finite difference method is very easy, but it has limitations, many limitations like conservation. We cannot include. Okay. Otherwise, we have to include from outside conservation. Okay. So in that equation now, if you take del x equals to del y, then we get this equation. Okay. So if you rearrange this equation, then we will get final equation, that is t m plus 1 uh, comma n plus t m minus 1 n plus t m n plus 1 plus t m n minus 1 minus 4 times t m comma n plus q dot by k del square del x square is equals to 0. Please now appreciate one thing here. I have written this equation at a point, at a node. Okay, so we have to write this equation at all the nodes. Okay, so I have written this equation for t m comma n. So what I will do now? I will take t m comma n on the left hand side and remaining terms on the right hand side. So what I got the equation? I got the equation to find the temperature at the given node in terms of temperature at the neighboring elements. Okay. So we'll move further. Okay, so that I was telling to take now temperature on the left hand side is temperature at the given node is equals to what? 1 by 4 t m plus 1 n comma n plus t m minus 1 comma n plus t, means we can see in the diagram all these four temperatures are neighboring temperatures. Okay, so it is 1 by 4 into the summation of neighboring temperatures plus q dot by k del x square. Okay, so this is we can see it is very easy. Now, if there is no heat generation, this q dot by k will be what? 0. So we will get just the temperature at the given node is what? Average of surrounding temperature. Okay, so there is no heat generation. Okay, so it seems a little easy in that way. Okay, but it has drawbacks. That makes finite volume method better than finite difference method. Okay, we'll move further now. Okay. Now, what we do now? We'll just apply this 2D heat conduction. Okay. Now we can see the diagram here. On one side, there is 150 degrees Celsius temperature. On another bottom side, 300 degrees Celsius. On the right hand side, 200 degrees Celsius, and on the top, 100 degrees Celsius. Now, we have to split equally. So we get the four nodes, one, two, three, four. Okay, move further. Now what you do now? You just write the equation like at node number one. I just told it is the steady state heat conduction. So heat generation it is a steady state and without heat generation. So temperature at node 1, it is just average of surrounding temperature. So you can see the bottom diagram here. So it is average of what? 1 by 4 versus 150. Then next is T2. Next is what? T2. Okay. Then next is 100 on the top. You can see on the left hand side 150, on the right hand side T2, and on the top 100, and the bottom that is the T3. Okay. Now we'll go to the T2. I shifted point. Okay. We go to T2. T2 left is T1, right is 200, top is 100, and bottom is T4. I think I have taken. I think there is shift of temperature. I have taken the nomenclature as in the top diagram. Okay. I have taken the nomenclature from the top diagram. I think they are shifted. Okay. Then T3, see top diagram. So left is 150, right is T4, bottom is top is T1, and bottom is 300. We will go to the T4. Left is T3, right is 200, top is T2, and bottom is 300. Okay. So in this way, you can see evaluating is very easy. Okay. So please understand now there are two methods. Now we have got the equation. For simplicity, I have shown only 4 points, but in reality there are many points, maybe 1,000 points. Okay. Now there are two methods to solve this equation simultaneously, by the matrix method or the iterative method. Okay. So iterative method is fast. Okay. So generally we use the Gauss-Seidel method for iteration. Now move further. What I have done now, I have just written this equation in the Excel. Okay. We move further. Slide number 35. Okay. Now in the Excel, there is one option. Go back 35. Okay. So whatever you are in the Excel, there is option. I will just open the Excel now here. If you want to do there, you can do this. Okay. If you have a laptop, you can do this. Okay. So
So that actually you have to share the presentation from your side because we cannot see this Excel now because it's not there.
yeah. So what I did in the first cell, this top left is first, then second, then bottom left is third, and bottom right is the fourth lower. Okay, so what I did, I written the equation. When I write the equation, Excel gives the error. Why it gives the error? If you see, go back in the slide number 34. So you can see here in the T1, T2 is asked, and in the T2, T1 is asked. If you see the T1 equation, it asks T2. And if you see the T2 equation, it asks T1. So it is a cyclic reference. So it gives the error in the Excel. And then we have to accept that error. Okay. It will ask there is cyclic reference. Okay. And in the Excel, what you do, you go in the uh, Excel options. You go in the Excel option and you go in the formulas in the Excel option. You go in the, you can see, you show the PPT. I think next PPT I have shown there. Okay. If you go in the start of the Excel sheet, okay, start button, round button, you can see the round button there. Okay. And if you click there, round button, it will ask the Excel options. And in the Excel option, there is second option, formulas. In the formulas, it is also shown in the PPT. In the formulas, what we have to do is enable the iterative calculation. Default, the iterative calculations are off. Please understand. When you say enable, then it asks a number of iteration and the error. Okay, it will ask error as well as number of iteration. Okay, so whatever iteration you want to give, so the Excel can also do the iterative calculation. Please understand it. Okay, so whatever a calculation I have obtained, it is because of the iteration. So when I started in the fourth cell, I gave the 0 0. Everywhere I started with what? 0 0. Okay. Then I went and switch on the iteration. Then they give me this temperature distribution. have to just check whether this temperature is right. If you see the node number 1, it is on the left hand side 150 and right hand side 200. Okay, so your temperature should be in between these two range. Okay, 150 and 200, so it is 156. Okay, now go to the node number 2. It is existing on the top 100 and the bottom is 300, and this is the 168. So okay, it's maybe it's okay. Okay, this way we have to also cross check. So what I have to say here, we can do the iterations in the Excel itself. Okay, no need to make program. Now we can move further. Now here we saw the case where the everywhere temperature was specified. Okay, but what happens in the real case? Not every time the temperature will be given. There will be convection. There may be some insulation. There may be some radiation. Okay, so this we have to take into account. So to treat the boundary condition, we have to take the help of the one method called as energy balance method. Okay, what we need to do is we need to take the help of energy balance method. Okay, while taking into account energy balance method, we can say convention we have to follow, that heat is to be directed towards the node. Okay, otherwise what will happen, this plus minus sign to be adjusted properly. Otherwise somewhere it will be added, somewhere it will be deducted, and your we can say energy balance will not be maintained. Okay, so this convention we have to take into account. So what we do at the boundaries, we define some cell. Define some cell volume, and then we write the energy balance, like heat conducted plus convected plus generated plus radiated equals to 0. All heat entering into the element will be 0. Okay, and one more thing we need to maintain here, or assume here, that temperature difference in particular element we have taken is temperature difference is constant. Okay, so now we'll move further. Slide number 37. So consider the steady state heat conduction. Okay, now we'll take the first case with the steady state heat conduction in the L-shaped solid body, whose cross section is shown in the diagram. Okay, heat transfer in the direction normal to the plane of the paper is negligible. Means it is a 2D heat conduction. Okay, and the thermal conductivity of body K is given 50 watt per meter Kelvin. Heat is generated in the body at Q dot 2 into 10 raised to 6. The left surface is insulated and the bottom surface is maintained at some temperature, that is a 90-degree. Entire top surface is subjected to convection, means on the top side there is convection. Okay, and on the bottom side temperature is given 90-degree. On the top the convection is there and it is subjected to the air of temperature T infinity. Okay, and heat transfer coefficient H is given. Heat transfer coefficient H is given, that is 80 watt per meter square Kelvin, and right hand side there is a heat flux, that is the heat per unit area, that is 5000 watt per meter square, and there are 15 nodes with delta x and delta y equals to 1.2 centimeter. Okay, now what you are needed is we have to find the temperature at the different nodes. Okay, so here we have to use the finite difference method. Now move further. Now we have to show the diagram. Next slide, there is diagram. You can see the diagram. On the left hand side you can see the insulated, right hand side there is some heat flux Q, and the bottom there is 90-degree. and on the top there is a convection to the surrounding with the h is given and T infinity is given. Okay. Okay, now we'll move further. Now we already know now that internally how to treat the elements. Okay, but how to treat the nodes. But now here, what we'll add is how to treat the boundary condition. That is our aim here. Now we'll move further. Slide number 40. Okay. Now you can see here, just I've started on the left hand side, there is node number 1, 2, and 4. Okay. So what I did here, I made one element, which is just between the midpoint between the 1 and 2 and midpoint between 1 and 4. So I made this element. Okay. Now we have to do is we have to apply energy balance on this element. Okay. Please understand here. Okay. So I can see here I have written in the red color A, B, C, D. Okay, these are the five hits which are going inside the element. So A is what? A is the heat generated. Okay, so heat generated is what? Q dot into the volume. So this half length is what? Del x by 2 along the x direction, and in the y direction what? It is del x del y by 2. And in vertical direction we are taking as a unit length, that is a 1. Okay, so this is A is what? Heat generated. Now we'll see the B. Okay, now B is the face. Okay, so what will be the area in the B? It will be del y by 2 into the 1 meter. Okay, in the depth. Okay, this is the area. Now as this B, you can see on the B side there is the insulation. Okay, so insulation means what? Heat flux is what? Zero. Heat flux is what? Zero. So how we write heat? If the heat flux is known, we write Q into the area. Area is what now? Del y by 2 into 1, that is the del y by 2 into the heat flux Q. But please understand here, Q is what here? 0. Ultimately, this will become, second term will be 0. Now move to the C here. Heat conducted in the vertical direction. Okay. So what is the area of this face? For the C, the length is what? Del x divided by 2 into depth is 1 meter. Okay. So it is we have to write now Fourier's law. It is K into area. I told it what? Del x by 2 into 1. That is the del x by 2 into temperature gradient. Okay, so temperature gradient is what? Node T4 minus T1 divided by distance between these two nodes is what? dy, del y. Please understand what we assume here, that temperature gradient is constant along the element. Okay, although it is on the left hand side, still we are assuming that gradient is constant, that is T4 minus T1 divided by del y. As I mentioned that whatever node we are treating, we have to take on the right hand side. Okay, like T4 minus T1, we have taken T1 as a minus. Okay, because node is what? I am treating the node number 1. Okay, if I go to the node number 2, then I have to take minus Q2 while writing conduction, convection, anything. Okay, now we'll move to now C where C taken. Now we'll move to the D. D is what? It is again conduction from 2 to 1. Okay, so we'll write that a K into the area is now vertical del y by 2 into depth, that is 1 meter, that is K del y by 2 into the temperature gradient, that is T2 minus T1. And what is distance between T2 minus T1? It is del x. Okay, so So T2 minus T1 divided by del x. Now I can write T1 minus T2 or T2 minus T1. But what I told you that while dealing any node, the local temperature should come always in the subtraction. So it should be minus T1 here. Okay, that convection we are using. Now you see the heat flow E, red color shown. So is what A we know now here is a convection. You can see outside there is a H is given, T infinity is given. So here there will be convection. Okay. So the area will be now length is what element length along the x. It is del x by 2 into the 1, that is del x by 2. Okay, so it is a HA, A we know del x by 2 into T infinity. Surrounding temperature is what? T infinity minus local temperature, that is the T1 equals to 0. Okay, now we simplify this. We know that left hand side heat flux, as it is adiabatic, it is 0. So by rearranging, I get this equation. Please understand here concept is what? Writing the equation on the boundary node. So we have written the equation on the boundary node 1. Okay. Now what I have to do? I have to rearrange this equation, make the T1 on left hand side and remaining things on the right hand side. So we got the first equation. Okay. We can now move next slide. Now you can see here node number 2. Here as we have taken the two quarter elements. Okay, so our the cell form is from the midpoint between 1 and 2 to the midpoint between 2 and 3 and midpoint from 2 and 5. Okay, so again I have depicted here A, B, C, D to know what is the A. A means what? First equation in the my whatever equation written, first component. Then B means what? Second component in the equation. Now we will see A component. It is what? And the cell, that is the heat generated. Now you can see along the X it is a full, so
Uh,
it is a del X.
Excuse me.
Yeah.
There's the one question by the Sayas Emily that which numerical method, finite element or finite difference method, is best for simulating air pollution problem?
For simulating.
Air simulate air pollution problem. First,
Oh,
he want to know that
so
which method is correct. I mean, finite element
yeah.
or finite problem.
Yeah.
Finite the difference. Sorry.
Please understand, if you see the CFD, where we simulate fluid flow and heat transfer. Already, actually, the method we started was finite difference, but it has limitations, finite difference, okay? To deal the complicated geometry and deal the conservation. So the base method for CFD is the finite volume method, and it is mostly used for all the CFD software. Okay, but we learn this finite difference method because it is easy and we can appreciate how the things happen. Okay, that is the only the meaning here, because I also not support the finite difference method. Okay, so now here actually what we are doing here now, we are dealing the different boundary conditions. Okay, for the boundary nodes. Okay. Now we can see here what I have written. A is the heat generated in the element. It is Q dot into the volume. So bottom length is delta x and vertical is del y by 2. Now you can go to the B. You can see B is what? Heat conducted. Okay. From 1 to 2, what can happen is a heat conduction. So I can write Fourier's law Ka. A will be now what? Del y by 2 into depth is 1 meter, and then temperature difference, that is T1 minus T2 divided by the distance between their 2 points, that is the delta x. So I have to write T1 minus T2. Whenever I go for any elements, I have to write subtract that temperature for their node's temperature. Okay, to maintain the sign convention. So I am taking T1 minus T2. I am not taking T2 minus T1. Please understand it. So to maintain the sign convention, to maintain the heat balance. Okay. So I am writing T1 minus Q2 divided by del x. Del x is what? Temperature distance between the temperature T1 and T2. So it will make what? Temperature gradient. I will move to the third part, that is the C. C is also heat conducted from uh, 3 to 2. So I will write uh, K del y by 2 T3 minus T2 divided by del x. Then comes part number E. You can see part number E, it is on the top side and there is a convection. So we have to write Newton's law of cooling here. That is the HA. You can see area here. You can see it is a full length. So it is a del X into temperature, surrounding temperature minus element temperature, that is node temperature Q2 is equals to 0. Again, this equation we have to rewrite in a such way that T2, that is the node's temperature, will be on left hand side, remaining thing will be on the right. Now we'll go to the node number 3. Again, we have to create the element. Why we create the element here? To write the equation. Okay. Generally, this element is 1/4, but in node number 2 we made the 2 elements of 1/4 size. Okay. But here we made only the 1/4. Okay. So between the node 2 and 3, we taken the point. Between the node 3 and 6, we taken point and created the node. Again, I have given the A, B, C, D to indicate the different heat components. So A component is what? Conduction. Conduction from bottom side 6 to 3. Okay. So how will write Ka? Area is what here now? Horizontal length is what? Del x. But it is half the length. So it is del x by 2 into vertical length is 1. So it is a T6 minus T3 divided by del y. So please understand T6 minus T3 divided by distance between that. That is the distance is what? Del y. So that is what? It is a temperature gradient. I'll move to the part number this is the A. I'll move to the part number B. It is again conduction from 2 to 3. So I'll write Ka. A is now here what? Del y by 2 into 1, that is vertical length, vertical in the direction of paper, into the direction of paper, into T2 minus T3 divided by del x. Okay. Plus now will be the C. C you can see C is again convection. Please understand. Okay. This side 3 6 side is also subject to the convection. So I write HA. You can say A is now what? Del y by 2 into 1 into T infinity minus local temperature T3 plus now next component is D. D is again convection HA, but HA is now what? Delta x by 2 into 1 into T infinity minus T3 plus next component is what? Heat generated in the element, that is Q dot del x by 2 into del y by 2 into 1. Okay, that is the volume. Q dot into the volume equals to 0. Again, what we have to do is take P3 on left hand side and everything on the right hand side. Okay, so we'll move further. Slide number 43. So if you see here, again I am taking the two quarter elements here. Okay. Now on the left hand side there is the insulation. Okay. And other things there is a what? Conduction. Okay. So there will be four high heat components. One will be convection, and remaining three will be one will be heat flux, three will be conduction, and one will be heat generation. Okay. So I'll start with the A. A is what? Insulation. So I'll write what? Q into area. Area is what now? Del Y into 1. So it is del y. Okay, vertically it is what? Double. Plus B is now what? Conduction. So it will write Ka del x by 2. There is area into the T10 minus T4 divided by del y. Plus then you see the C. C is again conduction. And we have to take the K into area. Now we can see the area is double of the del y by 2. So it is a del y into T5 minus T4 divided by the distance between two nodes, that is the delta S, that will give the temperature gradient. Now I move to the D. D is heat generated in the element. Q dot into the volume. Q dot into what? Volume. Please understand here, it is a del X by 2 into del Y. I accidentally written 2 here, but it is there no 2. Okay. Del X by 2 into del Y. Okay. Del Y it is complete. Okay. Vertical direction. Plus, now we'll see the last component E, that is conduction from 1 to 4. So it is a K del X by 2 into T1 minus T4 divided by del Y is equal to 2. Now here what will happen as for part A, as it is insulated Q, its flux is what? 0. So that term will get 0. Okay. Now same thing again we have to do. We make T4 on the right and everything on the T4 on the left and everything on the right. So we got the equation for what? T4. And we can move further. Okay, similarly, we can do for boundary conditions like here for node number 6, as it's a corner. We have taken the 3 quarter elements. Okay, L-shaped element we have taken, and we are applying the boundary condition like A, B, C, D, E, F. Okay, total 6 components we have taken here. Now move further. 45. Okay. Similarly, here one corner element is taken. That is the point number, node number 9. Okay. So in this way, we can make we can make the equation for all the elements. We know how to create equation for internal elements. Now we saw how to apply the how to create the boundary elements, how to form the equation for boundary elements. Now, as there are 9 points, we can get the 9 equation. We can move further. Okay. Before moving further, what happened in this problem? The radiation was not taken. Okay. To just tell you how to take the radiation into picture. Suppose on the component A, there is a radiation. Okay. You can just say on the top of 8 and 9, there is a radiation. How to take this radiation into account? So we have to write NECT of this surface, 8, 9 surface into the sigma. Then size is of this element is along the x-axis del x by 2 into T infinity raised to 4 minus T9 raised to 4. Like this we have to take if there is a radiation. Okay. As I've taken the radiation, I just shown for example. Now move further. Now after doing this, what we'll get? We'll get the equation at the different nodes. So I got this equation at the 9 nodes. Now same thing I will do now. I will go to the Excel. I will write this equation. Again, it will give us circular error message. I will switch off that, and then I will tell the Excel to start the iteration by going into the equation. There is a button. Okay. So now move further. This equation now we have to solve with the either program or with the help of Excel. So I have solved with the help of Excel. Okay, I have taken 100 iterations. Okay. For doing manually, it takes a lot of time. But if you go with the Excel, it is a matter of second. Okay, it immediately solve 100 iteration, 1000 iteration, any iterations. Move further. So what we saw is steady state two-dimensional heat conduction with the heat generation. But there can be case where the heat conduction may be transient, means temperature changing with respect to time. Okay. Now, when we solve transient equations, okay, then which parameter we have to take is the time step. Okay, you might have seen if you use the CFD, we use the CFL criteria for transient simulation to decide the time step. Similarly, here there is one equation to decide the time step. We can move further now, as we are running, I think, out of time. Okay, so if I write transient equation, then it is left hand side is very much similar to what we did. Okay, just now. Only on the right hand side, there will be change of internal energy that is to be included in the same problem. Okay, so I can move further. Before moving further, I will tell there are two methods in the transient conduction. One is called as explicit method, and second is the implicit method. In the explicit method, what we do, we use the value of previous time step to calculate the value of variable at the current time step. Okay, so it is easy. Explicit method is easy, but there is instability associated with the explicit method if the time step is not selected properly. And there is a implicit method where we have to directly solve simultaneously solve the equations. So it is easy. Explicit method is easy, but we have to take care of the time step. So we'll move further. Okay, so we have to decide time step, and whatever time step is guided, we have to take less than that. We move further. Okay. So here we define what is called as the mesh Fourier number, that is denoted by tau. So I will describe the tau in a such a way, like if you see the equation, tau is alpha divided by delta x square by delta t. If you see the unit of alpha, that is the thermal diffusivity. What is the unit? Meter square per second. So similarly, if you see that quantity below the alpha, it is a delta del x square by del t. So its unit is also same. So I call alpha as actual thermal diffusion, and I call del square x square by del t as computational thermal diffusion. Please understand. Okay, I call it as what? Computational thermal diffusion. Okay, so theoretically, if you want uh, accurate answer, what should be there? Your computational thermal diffusion should be faster than the actual thermal diffusion. Then and then your solution will be correct. Okay, so that's why we have to select the tau. We have to select the time step in a such way that tau is less than half for 1D and less than 1 by 4 for 2D, and you can move further. For 2D, tau should be less than 1 by 4. So from that condition, we can find delta t as del x square divided by 4 alpha. Okay, it means you calculate del x square divided by 4 alpha, and you select the del t less than that value. Okay, for 3D, tau should be less than 1 by 6. That is, delta t should be less than del x square by 6 alpha. So in this way, we have to decide a time step. If you take more time step, what will happen? Your computational diffusion will be slower than your molecular thermal diffusion, and your answer will not be correct. Move forward. Please move further. 57. Now, what I'm telling you, the same problem with now it will be in a transient mode, and we will use explicit method. Okay, move further now. Move further. 59. Please now, same. Now I am applying the boundary condition, but now in the boundary condition, there will be now change. What change will be there on the right hand side? I will write MCP delta T by delta T. Okay, what I am writing MCP delta T. So rho into the volume here del x by 2 into del y by 2 into 1 into C into the temperature difference. So it is a T1 I plus 1 means the temperature at new temperature minus old temperature. I means old temperature, I plus 1 means what? New temperature divided by delta T. Now if you see the left hand side here, all the temperature I have replaced as what? I. Means all temperatures are old. Only on the right hand side there is one temperature, new temperature on the right hand side, and second temperature is old temperature. So what I will do here in transient case, I will keep new temperature on the left hand side and remaining all the old temperatures on the right hand side, and then I got the equation for particular node. Now move further. Move further, yes. Now similarly for node number 2, you can write the boundary condition. Only change is what? Slide number 60. Similarly, for node 2, the same equation I am writing only in the case of temperature on the left hand side. I am writing suffix uh, I, superscript. I am writing as a TI, meaning it is the old temperatures on the left hand side, and on the right hand side I am writing MCP delta T. Now here volume, if I say it is two elements, two into quarter elements. So it is 2 into del x by 2 into del y by 2 into C. Okay. So temperature difference on the right hand side, I am writing T2 I plus 1. I plus 1 means what? New temperature minus T2 I. T2 I means what? It is a old temperature divided by del T. So what I will do now? I will take the new temperature, that is I plus 1 on the left hand side, and remaining everything, that is old temperature on the right hand side. So I got the equation for node 2. Similarly, I will write equation for node 3, slide number 61. Okay. Similarly, I will do same thing here. Make the new temperature I plus 1 on the left hand side. Similarly, you can go for next slide, 62. Okay, you can do here similarly and move further now. Similarly, you can do for this element. Okay. What change we have made here is on the right hand side we are writing what? MCP delta T. Okay. Move further. Now, if you rearrange this equation, we can rewrite the equation in terms of tau. Okay. Move further now. Okay. So, with the delta t as 10 seconds, I get this equation. Okay. Now here, there are old temperature and new temperature. On the left hand side, new temperature. On the right hand side, there is a left hand side there is a new temperature. On right hand side, there is a old temperature. Okay. So like here, will not do in the same loop, but now if you do in the Excel, we have to go in the next column. Okay, you can show the next slide. So here there are 9 nodes, so there will be 9 equations. Okay. Uh, Now what I did, if you see the table, this is the Excel screenshot I would pasted, a right hand side table. See the right hand side table, first column I am showing the node number. Then second column, what I did, I taken the solution from a steady state simulation. Okay, I've taken the temperature from the steady state simulation. And then third column, it is after 1 delta T temperatures. So you can see the temperatures are not changing. Okay, steady state simulation, if the steady state simulation is what actually, uh, steady state simulation, if you see, by running any transient simulation for infinite time, we reach to one solution, that is the steady state solution. Now, already the steady state is achieved, and if I run it as what unsteady, it will give the same answer. Okay. So next, what I did, go to the next left table. So what I did, initial condition as a 0 degree Celsius. Okay, and on the bottom I have taken delta t as time step as 10 seconds. So in the first time step it gives this temperature 5.7. Then if you go to the next time step it gives 18.4, 18.5, 22.1, like this. So if I repeat many time step, the time will arrive that I will get what, steady state solution. Okay, I will get the values same as the steady state solution. Okay, next.
So here with this delta t, with the by chance a person will take a delta t 2 seconds or maybe 5 seconds, maybe a 10 seconds. So will this
Yeah,
delta
yeah.
t create the
Like,
problem?
yeah,
Will
yeah.
this
Please
delta
understand.
t will change the
Uh,
answer?
yeah, yeah. Like here, we have to we have to follow that condition that tau should be, as it is 2D, tau should
Okay,
be
that
less
condition.
than
That
1 by
condition must
4.
be followed.
Yeah, that condition should be followed.
Okay,
And
okay. So as far as this is
delta
the
t
less
equals to
than 1 by 4,
delta t equals to 10 is the maximum value. 10.2 something it is coming. So I have taken the lower than that, that is 10. So we have to take delta t either 10, 8, 6, 2, 1, less than 10, anything you take. Okay.
so my mean to say for less than 10, if you are one person is taking 2, other person is taking 4, will their answer be same?
Yeah. After infinite iteration, their answer, final answer will be same.
In okay, okay.
Like if you take the time step 2 seconds, you take more number of time interval to reach to the steady state solution. Okay. If you take 10 seconds, then your solution will be faster to reach. Okay. I will move further. Next slide. Slide number 66. So now, what I am doing now, I am giving the task to the participant. Move to the 67. Slide number 67. Participant can take the screenshot of this 67 and 68, and they can try with the Excel. Okay. I will send the answer to the Professor Rajkumar Arya. Okay. They have to try this themselves. They can take the screenshot of slide number 67 and 68. And they can try, write the equations and then solve with the Excel. So here one is how you apply at the node boundary conditions. Okay, for internal load, we know how to write. For boundary nodes, we have to write again equations and then rearrange the temperatures in a such way that for steady state, node temperature will be on the left hand side. For unsteady, new time temperature will be on the left hand side. And then we get the equation. That equation we solve by iterative method. So I will send the answer to the Professor Rajkumar Arjan. If you are interested, you can collect that. So I will say thank you to you. If you have any questions, you can ask. So I will
So,
again say one thing here. Finite difference method is not good, but as an initial learner, we can go this and appreciate how the things happen. That is the only thing I want to say.
so any question from participant side? Any question from anyone? But why do we say all the time that why do we say all the time that this finite difference is not means correct something? Is there any
Yeah,
particular reason for
I
that?
will say finite difference is not a wrong method. Okay, it has some
Okay,
limitations like to handle the complicated geometry there is problem. Okay, and second thing is
okay.
conservations are not added. We have to take care from external. Like while giving the boundary condition, we have taken the care by defining the volume there and writing the equation. Okay, like this
Hmm.
conservation we have to ensure there by doing some additional equations in there. Okay. Main thing is that it cannot handle the complicated geometry. Okay, that is the main
So
issue.
it okay. So in your Excel sheet, you have said in one of the column you have just wrote the variables numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And next column you might have wrote all your equations, right? Equation for T1, T2, T3,
I think I
T3.
lost connection.
Is it correct?
Maybe you repeat the question. Please repeat the question. I lost the connection. Hmm.
In for Excel sheet, uh, in first column, actually you wrote your 1, 2, 3, 4, 5, 6, 8, 9. So those are nine
No, no,
variables, I think,
they are
nine temperatures.
nodes. Node number one, two, three, four, five. There are nine nodes. I have written
They are
nine nodes here. And then first
okay.
column, initial condition.
So those are the
Yeah,
nodes number. In column 2,
it is a initial condition. Uh,
because I want to learn it, because I generally solve all these by MATLAB. So if the Excel can save my time, it would be good for me.
yeah, it is very fast. Yes. And what I did now in the first column, I have written the equation. Okay, in terms of what value, that is
Oh,
the
first column
column
you
number
have the
two.
equations, right?
First column
Column
is
number
the
2 or column
node
number 1?
identifier. Column number one is what node number for my purpose. It is not for their purpose. First column is the initial, second column is initial
Okay.
condition. Okay, and third column, what I have done, I have written the equation there in terms of second column. Okay. Now what I have to do, I have to just
Okay.
copy that third column in the next columns. Automatically, it will take care. We know that Excel, no? If I copy column number
No,
three,
we have
yeah, if I take the
hmm.
column number three and paste in the four, it will automatically take the equation. So its starting condition is what? column number 3. Like this, if I copy many times, automatically I get the value at that iteration. Are you
Okay,
getting
okay,
this?
okay, okay.
Hello?
Any other question from participant? Yeah, yeah, it's fine actually.
Yeah.